This is the lecture for Module 1 of Unit 7. Unit 7 is on electrochemistry. You will see that this brief unit is closely related to the thermodynamics unit of this course. In this module, we introduce electrolytic cells and the standard cell potential. Alright, what is the idea of electrolysis? Alright, consider a reaction in which aqueous copper chloride, a solution of aqueous copper chloride, separates into solid copper and chlorine gas. Alright, this reaction is not spontaneous. You won't see it spontaneously happening in your laboratory. You could look in tables of delta G's and calculate a delta G for this reaction. You'll get a number greater than 0. However, this reaction can be made to happen if electrical work is applied. In general, it can be shown that if delta G is greater than 0 for a process, you can make it happen within the system by applying work equal to delta G. Likewise, we'll see that if delta G is negative, delta G can be used to provide work. But in this case, we would have a direct current source like a battery connected to a power supply, for example, and that causes this non-spontaneous reaction to occur. For example, here we see in one electrode is immersed into the copper chloride solution. This anode, where oxidation occurs, is the place where chloride ions come to give up electrons and become chlorine gas. The chloride is oxidized at this anode, and the chlorine gas can escape from the water. Meanwhile, over here, copper has electrons added to it at this electrode immersed in the water called the cathode, and the illustration shows copper depositing, solid copper depositing on the cathode. Electrons are removed at the anode, flow through this circuit, and are deposited at the cathode. And this is accomplished by the power supply, which is supplying the voltage or the necessary to make this occur. Alright, so again, electrons are flowing from the anode to the cathode as a result of the application of work, in this case an electrical voltage from an outside source. Okay, so again, the anode is where oxidation occurs, or electrons are removed in this case. We can write a redox half reaction for this. 2 chlorides goes to chlorine, produces 2 electrons. So, cathode is where reduction occurs. Electrons are added. Here copper cations are meeting with electrons to form copper solid. The net reaction is the sum of the cathode and the anode. The redox half reactions that make up this redox reaction occur at opposite electrodes or different electrodes of the electrolytic cell. Notice this equation is already balanced for us to add these half reactions together. The electrons lost here and the electrons gained here are the same. And of course, you know electrons gained must equal electrons lost. Alright, let's consider another example. This is an electrolysis cell for the electrolysis of water. Again, oxidation occurs at the anode. The oxidation of water produces O2 plus 4H plus 4 electrons. Reduction occurs at the cathode. Electrons are added to water to form H2 and hydroxides. Summing the half reactions, well, yeah. Okay, and so we have gas evolving at both electrodes. And, products within the solution include protons and hydroxides. The net reaction, oxidation at the anode, is added to reduction at the cathode. You have to multiply this by 2, so the total number of electrons exchanged in this reaction is 4. And in this net reaction, 6 waters form into an O2, 2 H2s, 4 H pluses, and 4 OHs. Of course, we expect that in solution these will reunite to ultimately reunite in the tank above to produce water. So the net result of the application of work is the non-spontaneous reaction. 2 waters goes to O2 and 2 H2. Alright, so you know that this reaction is non-spontaneous. Alright, let's look at some concepts. You can do some stoichiometry with these electrolytic cells, and in some cases these electrolytic cells are used to produce material. The current motion of electrons through a wire is referred to as is measured in units of an ampere. Charge is measured in coulombs. A coulomb is the charge of electrons resulting from allowing a current of 1 ampere to flow for 1 second. Or just to say, 1 ampere is 1 coulomb per second. A mole of electrons, 1 Faraday, is 9.65 times 10 to the 4th coulombs. Right, here we relate the physics concept of coulomb for charge to the chemist's ideas about moles. A coulomb of charge is the equivalent of a mole of electrons. Right, this allows us to relate chemistry to current. For example, in a copper cell, how many grams of copper can be produced in 15 minutes with a current of 30 amperes? Right. If we can calculate the number of electrons that have passed through this current, or at least moles of electrons, we can relate that to grams of copper. I recommend attempting this exercise before continuing in the presentation. Alright, in the copper cell, how many grams of copper can be produced in 15 minutes with a current of 30 amperes? Minutes are an inconvenient time unit here. We can convert them to seconds. And then coulombs per second with amperes times seconds gives us 27,000 coulombs. We can convert that to moles of electrons. That's 0.28 moles of electrons. Two significant figures. Convert that to moles of copper, and then by multiplying by the molar mass, convert moles of copper to grams. Now, I have shown each of these calculations one step at a time. There is no reason in principle not to combine all the steps in one stoichiometric calculation. Right, but you see, current and time can be related to moles of electron, and hence to moles and grams of substance in the electrochemical reaction. The voltage, which in this case will be the voltage needed to apply to make the reaction go, can be calculated under standard conditions using standard cell potentials. I mean, these are had from data tables. This link represents a stable link to some electrochemical data tables. By standard, we mean all the concentrations of solutes are 1 molar and the temperature is 25 Celsius. All right, under standard conditions, say which we'll see is actually 1 mole of copper, 1 mole of chloride, in spite of the stoichiometry of the situation. You can determine a standard voltage for the cell by taking standard potentials from the table and subtracting the reduction from the oxidation. All right, again, the fact that there are 2 chlorides produced, or any stoichiometric relationships are not tracked in this. Simply take the difference of the 2 cell potentials and we have a standard cell potential. Notice that it's negative. This is what you see for non-spontaneous reactions. Under standard conditions, you would apply a voltage of 1.02 to make the reaction occur. Right, we will learn in the next unit how to correct for non-standard conditions and how to build electrochemical cells out of spontaneous reactions. If the reaction is spontaneous, electricity can be made to flow spontaneously, and we have a source of electrical energy. In other words, this can be used to construct batteries. All right, this discussion will continue in Module 2.